All right, welcome to Hyperstition number 10, next generation lithium ion batteries. And I'd say like just to frame this conversation we're about to have about the science and chemistry of how to make next generation lithium ion batteries is that battery energy density is very likely one of the most important sort of civilizational levers that we can crank on to have a massive effect, a massive change on things. Creating higher density battery energy storage is not just like it's like mobility, autonomy, robotics, all of drones, all of delivery, right? Mobility and transportation, but also like grid energy storage. It's that, along with something like power density of actuators, perhaps efficiency of like a closed cycle gas turbine. Like these are, if you can get a few more percent performance in those metrics, it has sort of untold impact on like the economics of all of our industrial activity. So someone working on this deep in the weeds, in the trenches of next generation battery development is Ethan Loosbrock. Did I say that right?
Yeah, you did.
Okay, great. Well, thanks for being here, man. How you doing today?
Yeah, thanks for having me. I'm doing great. Yeah, excited to chat about batteries.
Yeah, that's great. Well, let's dig in. I'm curious and I'll disclaimer, I invested in your company myself because I'm super stoked on it. So I'll put that out there. But what are you building? What are you working on? Like, what is Oros? This isn't the snake eating itself, right? Ouroboros.
Yeah, it is actually. I mean, that's the inspiration for the name, and basically the idea is like, over the lifetime of the company, we cannibalize our own products with newer, higher energy density, cheaper batteries. And there's some, sort of double meanings because you cycle a battery but yeah, ultimately the goal of Oros is to build lithium ion batteries that store as close to 10 times the energy density of today's lithium ion batteries as possible. So we think it's theoretically possible. The sort of first step is going to be less than that. So for all of the skeptics out there, I'm not claiming we have 10x batteries today. I am claiming we have close to 2.5x today, but we will shoot for ultimately 10 times the energy density, and that's made possible through electrochemistry, which we'll get into a bit later. But yeah.
For context, like what is like the current performance metric to beat? Like it's some, and is the key metric, is it like kilowatt hours per kilogram, or what is the
yeah core? Yeah, exactly. So the 10 we're specifically benchmarking the like Tesla 4680, which is just under 300 watt hours per kilogram. So in batteries we use watt hours per kilogram because we're not yet in the kilowatt hour per kilogram range, but hopefully we'll get there soon. Yeah, so that's, I think that's one piece of it, but the other important piece is there are batteries that are higher than 300 watt hours per kilogram. So some lithium metal companies are around 400, maybe 450. Silicon is sort of around the same place, but neither of these are really at mass production yet. So they're and we can talk about why that is. But yeah, that we it's nice to have energy density, but if it's not mass production, you're not going to move the needle on a civilizational level, and so it has to be mass produced.
Right, and I think I've seen charts of like experimental research laboratory energy density can be extremely high, but then by the time you get to mass production, so let's get into it. I mean, I'm curious, like how does a battery work, right? Like let's refresh ourselves, and like how do you compete in the chemistry? Because I think there's probably the trade space is massive, right? Like the number of things you could do, the number of anode or cathode materials,
Right. Yeah. So we can maybe start with just what is a battery or a lithium ion battery. So a battery is pretty simple. You have an anode material and a cathode material. And so it's a little bit small on here, but right now the anode materials are carbon. So you have graphite on the anode, and then you have typically a metal oxide on the cathode. And then that's sort of your repeat unit. So you coat these materials with a little bit of carbon and a little bit of binder, usually 1 to 2% of each. The binder is being like a polymer. And then you coat them on metal foils, so copper and aluminum, and then you wind it up. So your repeat unit is like one big long foil, but it's wound up in these tight spirals. So on the top left, you can see sort of the cross-section view, how it fits in the can, and then if you unwind it, it looks like this singular strip. And then on the bottom there, what the illustration is basically like these carbon particles and metal oxide particles are roughly spheres. So you have your atomic structure and it sort of like layers together, but at the meso level, like the micron scale, it looks like little spheres that you're kind of packing together.
Mm-hmm. Mm-hmm. Let me ask some questions of this. So the battery is, you have the anode material, you have the cathode material, and I always forget this. I think it's like red cat or something like that, is like there's a reduction reaction and there's an oxidation reaction. And what are those, I guess? Like I know there's some kind of electrochemical potential, like voltage between one material and the other, but like what's happening physically to get energy out, I guess?
Yep. So this slide should help with that. So basically, like when you're moving current back and forth, you are moving electrons in the opposite direction. So when you make the battery, all of the lithium is in the cathode, and the lithium is your charge carrier. So everything stays in place, but the lithium shuttles back and forth. So when you put electrons into the cathode, you basically have you violate electroneutrality. So things generally want to stay at zero charge. So when you put electrons on them, it creates the opposite charge, so a positive charge on that material. So when you put electrons into the cathode, you get a positive lithium that then is attracted to the anode material. And so when you're discharging the battery, it does exactly the opposite. So technically you have reduction and oxidation reactions happening at both the anode and the cathode, depending on what part of whether you're charging or discharging. So like in lithium ion batteries, we do a lot of like half cell research where you'll just take an anode or a cathode to get fundamental insights into just that material. Because when you combine these two, you're actually looking at two sets of redox reactions. And so whatever you're looking at will be sort of through the lens of the other material. Mm-hmm. So when you combine them, and then like each material has its own, it's inherent to the structure. So, you can do like DFT calculations to try and figure out what voltage your material wants to sit at. But ultimately it's like pretty inherent to the material. And so, your cathodes will be up between 3 and 5 volts, and then your anodes will be as low a voltage as possible. So graphite is pretty low. It's 0.1 volts versus lithium metal. And so, we do
volts.
Yeah, go ahead.
Is that like how much energy it takes to strip an electron off its outer valence or something?
Yes. Yeah, it's not quite, it's like what energy level, when you strip it off, what energy level it's at.
Right. Okay. I'm trying to think of this like so the price of an electron, or the energy cost of liberating one ion off the material.
Right.
And so like a good battery has a big spread in terms of like the energy of the anode and the energy of the cathode, right? So it's like we get a big
Right.
voltage drop across between those two materials.
Yes, that's one part of that's the voltage part of the equation. The other part is the capacity, which we'll get into later. But basically, like the water analogy is a very good one, just for basic understanding. So you can think of it like you have a reservoir at the top of a hill and a reservoir at the bottom of the hill, and you want that hill to be as tall as possible. So you want your bottom reservoir to be as low as possible, so as low of a voltage as possible, and then the top reservoir to be as tall as possible.
Mm-hmm.
And then the size, so that the delta there would be your voltage. The size of the reservoir is like your capacity. The speed at which you can move water between them is like your current, or your C rate, which is kind of like a scale-free way of measuring current.
Mm-hmm. Mm-hmm. This makes sense. Yeah. Okay. So the art of battery design is really sort of constructing this electrochemical energy reservoir to kind of optimize the separation, the high and the low energy level, how easy it is to flow between it,
Yep.
and then its total capacity. Like, and I'm guessing these things kind of trade off against each other in different ways.
Totally. Yep.
Yeah.
Exactly. And then in the in developing these things, like it's sort of useful to understand it as like that repeat unit on this slide. It's somewhat useful to understand this as basically resistors in series. And so like whatever your biggest resistor is going to dominate. So if you want to increase the power or the current through a battery, you just need to figure out which resistor is the biggest and lower that the resistance of that piece.
Mm-hmm.
So let's see. I guess this is more like macro scale stuff. So I don't know if
I'm curious.
did you want to dive in on? Yeah.
Well, I'm curious here. Let's help get some intuition for, why lithium ion, right? Is there like any first principles kind of thing?
Yes.
Lithium is an interesting element.
So I have a slide on this later. Yeah, here we go. So if you look at the periodic table, there aren't many elements that are lighter than lithium. And so one of the important things to note is like lithium is doing the carrying of the charge. And so it's doing the work of the battery. So everything else in the battery is more or less dead weight. Like it's not really, because it has voltage associated with it and all that stuff. But from like a first, like eagle eye view, you want to maximize the amount of lithium and minimize the amount of everything else. Now, like there's been a lot of talk about sodium ion, potassium ion, these sort of alternative ions. And the challenge here is like all of these alkali metals are, and they're in the far left of the periodic table, which means they each carry one electron charge. So if you wanted to store equal amounts of energy per kilogram as lithium, you would need to make sure that for example, with sodium, you'd need to make sure that everything else in your battery is now 3 times lighter, because you're carrying the weight of the sodium. And then, with potassium, it's even worse. You need everything to be 5 times lighter, which for some parts of the battery that may be doable. But when you are looking at like steel casings or aluminum foils or polymer foils, it's very hard to get that sort of mass loss when these things are already like micron scale.
Mm-hmm, mm-hmm.
The other way you could go is looking at the alkali earths, like right next to the alkali metals. So you could those elements like magnesium and beryllium carry 2 electrons. magnesium, beryllium is super rare, so it's not very cost effective. Magnesium is has been tried once by a company called Pelion, but it's very hard to get to do 2 electron reactions because the number of side products you can produce, because there's 2 voltage steps, sort of explodes. So the 1 electron reaction is actually very simple and easy to manage. And then on top of it, like magnesium is more than double the mass of lithium. So you're still fighting against that mass. So your only options for lighter elements are helium, which doesn't want to be an electron carrier, and then hydrogen, which there's been 100 years or so of work on getting hydrogen to work in fuel cells or various different configurations, but hydrogen just doesn't really want to sit still and stay in the same place. So yeah, that's, I think,
hard to store at pressure. Kind of a terror. Yeah. It's like a bomb, basically. Like this hydrogen fuel cell. It's literally a bomb.
Yeah.
In some way. Okay, this is really good intuition. So I'm kind of like summarizing back into, in my mind, it's like really the energy density for watt hours stored in a battery. It's a function of like the charge to mass ratio of the ion that is passing from between the 2 electrodes. And so lithium, yes, is like, it's the lightest atom you can get that can favorably be ionized because it has 2 electrons in its inner shell and then 1 electron in the outer shell, so that outer shell electron sees some degree of like shielding of the interior from those first 2 electrons, so it can kind of come and go more easily. And then it's only atomic weight of 3, I guess, or is that right? Yeah, or no, atomic weight of 6, 7.
7, yeah, 7, yep.
Yeah.
Or 6, 9, yeah. Yeah, that's exactly right.
Yeah,
basically, like lithium is the best we've got, except hydrogen, and hydrogen is really annoying to work with.
Right. Yeah. And you mentioned something I think that probably is like the bane of battery chemists like yourself, which is side reactions. And like, let's get into this. Like, what do you mean by side reactions and this kind of thing?
Yeah. So if we're looking at like these reactions here, these are the reactions that actually are doing work in the battery. But because you have so many components, so you have, I mentioned the binder and the carbon on each electrode, so you're already at six components. And then in the electrolyte, which is sort of the liquid in between the electrodes that serves as like a medium for the lithium to move back and forth. So you have a lithium salt, sometimes 2, and then you'll have three solvents, 2 or 3 solvents, and then you'll have anywhere from 3 to 7 additives. So now you're up to close to 20 different components that are interacting with each other. So it's these things like tend to be a little bit squirrely. So you want to like make sure all of the work that you do in the electrochemical cell is one of the 2 reactions on this diagram, and everything else is inefficiency. So there's in the first cycle when you make a battery, we call that formation, and this typically happens before any consumer even sees the battery. But this step is like very important for ensuring the stability of the battery. So you do a very slow charge and discharge, and those additives that you put in, if they're working properly, they'll make a thin film over the surface of the electrodes, and they will passivate the electrodes so that there's no continued reaction, or as little continued reaction with the electrolyte as possible. And so like typically the best batteries out there, so like if it's an NMC graphite cell, they will lose a full 10% of their energy that first cycle, and it's irreversible because you're consuming some of the lithium to make this layer. And then after that cycle, or maybe you do a few formation cycles, but after that first cycle or first few cycles, your efficiency, your coulombic efficiency will be at least 3 nines. So 99.9 for the best cells, it's, you're looking at 5 or 6 nines. And so basically, like, yeah, that's, I guess,
what does that
where
mean? Nines term. I think I heard you use this before. Like coulombic
yes.
efficiency, is that like just resistive losses due to current flow?
So there's two types of efficiencies in batteries. One is coulombic efficiency, which is just coulombs moving back and forth. So this is your electrons and your lithium that are sort of like going to meet each other on each side of the electrode. So it's basically how much current or capacity did you put in, and how much did you get out? That's your coulombic efficiency. Energy efficiency just is the coulombic efficiency with your voltage losses. So on one of these other slides I have, so this is like a charge discharge curve for LFP and NMC, which are two of the big ones, and then this is LMFP, which is kind of in development for some manufacturers. But basically, you can see there's the charge curve is the top curve on all of these, and then the discharge is the bottom. So you actually lose a little bit of voltage as well in each cycle. But that's more of a thermodynamic problem. It's something that you can minimize as much as possible, but you're likely never going to get to zero. Coulombic efficiency, however, is electrons and lithium ions moving back and forth, and so you can get that to many nines. I think I don't have it in the slides here, but maybe I can pull up. I have another diagram that does a really good job of explaining why these nines matter.
Just reframing. So coulombic efficiency, this is like any charges, basically any charges that are not part of this main reaction of charging, discharging, they end up getting bound up with these side reactions that.
So they can go to all sorts of things. So there are, they can be lost as heat if your cell is not made well. They can be lost to side reactions. That's a big one. They can be lost to particle cracking. They can be, so that's sort of like a mechanical loss in a way. And there's other types of mechanical losses. So if your welds aren't perfect, you'll lose electrons there. So it can be lost inside or outside the cell. There's like, so there's many different types of losses, but assuming a very well-built cell, most of the losses should come from side reactions.
And the sort of figure of merit is like 3 nines or 4 nines as like a good battery or a good.
Maybe I can show this here. Can I share something?
Yeah, sure. I can take this down. We can look at the sci-fi background. This is the future. If we had Ethan's high energy density batteries, we would have like geodesic megastructures and live in a pastoral setting.
So can you see that? I don't.
No. We just have this current plot. Yeah.
Okay. Let me see.
We can also just keep going through. I mean, you have.
Yeah, that's fine.
Skip through a bunch of this good solid battery content. YouTube is thirsty for battery content. What is what is the limiting factor here? So, 'cause I think we have a good handle on the kind of fundamental chemistry of a lithium-ion battery. Lithium is the best element to use. It's the highest charge to mass ratio. We're targeting this one reaction, a bit of voltage sag, a bit of lost current from side reactions. And so when you say limiting factor, let's get into this.
Yes. So just before that, maybe I'll just like I have the figure up, but I'll just talk through it. So basically, like for Coulombic efficiency, 99% Coulombic efficiency gives you, so it determines your cycle life basically. So Coulombic efficiency is more or less like how much charge you lose irreversibly each cycle. And so we determine that the end of life for a battery is where it reaches 80% of its original capacity. And so if you're looking at 99% Coulombic efficiency, it's like 50 cycles. 99.9 gives you it's about just under 300 cycles. And then if you get to 4 nines, so 99.99%, you're at 2000 cycles. And if you're at 99.995, then you're at nearly 5000 cycles. So the best automotive cells will be about 2000 cycles, so 99.99. And then, you know, for grid storage, you're looking at 5 to 10,000 cycles. So you're at typically 5 nines. So for like the hardest commercial applications, you're between 4 and 6 nines of efficiency.
And what are the hardest commercial applications? Is it like a smartphone? Like where is the big demand for performance?
Yeah, so automotive and grid are the hardest. They, for different reasons, maybe. Like grid storage is hard because extreme cycle life is hard, and they have they're very, very cost conscious. Automotive is somewhat less cost conscious, but still very tight on their costs. But they have a much higher performance threshold. So you know, you need, like, they're like trying to push for fast charging, and they're, you know, low temperature, high temperature, vibration. They have very strict safety standards. So there's a lot more you have to do to get a cell through validation in automotive than in grid storage, but they're both very challenging. And then I think easier than those would be consumer electronics generally. So those are like 300 cycles. So maybe 3 nines of efficiency. And then they're generally more forgiving on margins. And then, you know, at the bottom, there's sort of like defense and aerospace applications. So some defense applications need, you know, less than 10 cycles, sometimes only 1 cycle. And then,
right, like a missile, you know, or something.
Yeah, exactly. And then, you know, their margins are they're like something like 5 to 10 times automotive margins for a battery maker. So for Oros, that's where we're starting, and we're basically going in reverse order of what I mentioned. It's like defense, and then it's consumer, and then it's automotive and grid.
And I'm curious about that. So defense has they're the most willing to pay for like the highest performing thing, because they're there to win, right? Like it's a very binary outcome. And what about their performance requirements is easiest for you to address first? I'm curious about you guys, as you're kind of figuring out this battery chemistry. Like, is there parts of the battery chemistry design that are easier to pin down first, and then you move to the next kind of metric?
Yeah, for sure. So for us, the easier thing to pin down first is energy density. And then like the harder part that we're trying to sort of pin down now is like the power density. So, lithium ion batteries generally have like optimized all of their characteristics over the last few decades. And so, starting from scratch, like the power characteristics need to be tuned through electrolyte engineering or through, changing your particle morphology and size, or even just like cell engineering. So there are various ways of improving your power, but usually it's a combination of these things.
Mm-hmm, mm-hmm. And I'm curious on this kind of, I mean, I think maybe it was a couple of years ago, but people were talking about how we're going to hit this lithium supply crunch, and that we're all screwed, or the lithium prices are going to skyrocket. I don't know if they have, actually. I guess people keep finding more supplies of more lithium, or curious what is the limiting factor in terms of like rolling out these battery deployments at scale?
Yeah, I mean, I guess there's a lot of limiting factors there, I would say, but in terms of lithium supply, like I think lithium is relatively abundant. The actual challenge with lithium supply is like getting a mine permitted and up and running. So in the US, this can take like 10 years to do, even though we have like vast amounts of lithium in the US, and it's relatively competitive and economically. I guess beyond that, it's, I think cell manufacturing tends to be the most bottlenecked step in the supply chain. Generally, you can spin up pack manufacturing or system level manufacturing very cheaply, and it doesn't require a lot of like sort of like specific field specific knowledge. But yeah, I think, maybe a short step after that, after cell manufacturing, is refining. So that's also generally, it has more specific knowledge needed than like pack manufacturing, but is certainly easier than cell manufacturing.
Does Tesla is like fully vertically integrated in their whole battery stack, right? Like they have now their own lithium refinery and everything.
Yes. So I don't think they're mining the lithium. I think they're, so like there's two types of mining. There's brine and hard rock. So brine is like, there are these salars in South America primarily. There's one in California actually too, but the salars have like various alkali metal chlorides. So they have sodium chloride, lithium chloride, potassium chloride. And so they basically take these chlorides and they put them in evaporation ponds, and they drop out one chemical at a time. So they drop out the lithium in one pond, and then they drop out the sodium in another pond. And then you end up with like a lithium chloride that you need to then turn into either lithium hydroxide or lithium carbonate. And then that's what goes into the cathode. So they combine the hydroxide or carbonate with, if it's NMC, it's like nickel, manganese, and cobalt sulfates. And if it's LFP, there's a variety of different methods people are using right now, but you somehow combine it with like a phosphate compound and an iron. So sometimes it's like phosphoric acid, or, but yeah, people are changing that process quite a bit right now. But the hard rock then is just like a lithium carbonate that's in rocks, primarily comes from Australia. And then you have to like crush the rocks and leach it, and but then ultimately you produce a lithium carbonate. So that process, they don't typically produce hydroxide.
Okay. So there's different procurement methods for lithium globally, but it doesn't look like we're actually hitting this lithium supply crunch in that sense, where we're going to have our whole, like it seems like there's more deposits accessible or new refining methods that are.
Yeah, I think that's right, and I mean I think like um, you know lithium. I think we're going to basically see something akin to the early days of the oil industry. So in 2022, there was a massive run up in price for lithium mined products, and then it spurred massive investment, and then the price crashed down, and now you're sort of seeing a little bit of a tick back up, and we'll see how high it goes, but some of the sort of subsidies and tax incentives and things have been pulled back both in the West and in China, so it may not be as dramatic as the last time around. But I think that'll probably continue. Like it'll probably continue to have a cyclical nature, where you have like a boom bust cycle, and the run ups incentivize further investment in the space, and make like less economical lithium sources viable, and then yeah.
Well, I mean, and like I said at the beginning, batteries are such a civilizational important thing. I'm curious, like, where is the room for optimization, or I guess like technical innovation? Because if everyone's using the same lithium ion, I guess, architecture or starting point, surely there is just a best anode and a best cathode, and everyone would just use those. Or is it actually like fragmented by use case and application, where it's like you want totally different material compositions depending on a high lifetime, high cycle battery in a smartphone versus some super high power output thing in a Stinger missile?
So I think today there's kind of a bifurcation. So you have like the very low cost, low energy applications using LFP and graphite, and then you have high energy, high cost applications using NMC 811. There is not much. I mean, consumer electronics uses lithium cobalt oxide now, but I think some of them are even switching to NMC 811. So I think
lithium cobalt oxide, is that referring to the cathode material?
yes. Yep.
Okay. And help us understand, like, the cathode is the thing that is giving up electrons and letting lithium ions flow in the electrolyte solution.
Yeah, so when you are charging the battery, the cathode is accepting the electrons, kicking the lithium out, and the lithium goes over to the anode. And then when you're discharging the battery, so when you're using it, the electrons go to the anode, and then the lithium comes back to the cathode.
Okay. And for battery noobs like myself, I know there's lots of work on the cathode. Is the anode chemistry somehow more understood, or less variable, or more fixed? Or when people talk about lithium battery, is it always in terms of the cathode material?
Yeah, so the history here is like the very first lithium ion battery was lithium cobalt oxide on the cathode and graphite on the anode. So this was developed, I mean, it was the cathode material came out of UT Austin. The anode material came out of like Exxon Mobil's research lab, and then kind of was further developed by some Japanese companies. But Sony commercialized the first battery for their handheld camcorders. So basically what we've seen since then is in the early 2000s. So from the start, graphite stores twice as much capacity as lithium cobalt oxide. So what that means is in every battery, you need your anode and cathode to be as close to matched as possible, because you can't have like one reservoir. You don't want one reservoir to be much bigger than the other one, because it's all wasted material and space and mass. So you want to match these two things as closely as possible. So because graphite stores twice as much capacity, you need 2 times the amount of lithium cobalt oxide in the cell to be matched. And so since then, like in 2010, roughly late 2000s, early 2010s, nickel manganese cobalt came on the scene, which is basically the same structure as lithium cobalt oxide, but they substituted out cobalt for nickel and manganese. So it's the same similar voltage, same capacity, but it's cheaper. So you could start to use it for automotive. You could use it for all sorts of new applications. In the early 2000s, a company called A123 spun out of MIT. There was a patent dispute with UT Austin's John Goodenough's lab, but ultimately A123 commercialized lithium iron phosphate. And at the time, it was not really seen as viable because it was worse energy density than NMC. So they didn't get that much traction, and they failed for sort of other reasons. But that IP was bought by a Chinese company called Wanshang, and then China basically continued working on it and commercialized it at massive scale. So those are the two sort of chemistries. That's why we're so focused on cathodes. Is all of these cathodes. So graphite's double the capacity of LCO or NMC. It's more than double the capacity of LFP. So in all of these things, your limiting factor is the cathode. And so that's what this sort of shows is inside the battery, the mass of the battery is 45% cathode. And then, you're at like 30 something percent anode, and then everything else is, I guess there's electrolyte as well, but the rest of the components are sort of meaninglessly small. And then, so if you go up one level, then you're at the pack level, your cells make up the vast majority of the mass of the pack. They also make up the vast majority of the cost of the pack, which I think is on this top left graph. So over time, the cost of the pack has basically come to be dominated by the cost of the cells.
Okay, and is this kind of like just economies of scale and manufacturing efficiency?
Yeah.
And it's sort of
exactly.
The cost or something.
Exactly. So that's what this right graph is showing. Is basically we started at, the materials costs were about 40% of the cost of cells back in 2015, and then by 2022, the raw materials costs were 70 to 80%. Today, it's even higher. It's like above 80% now. And so like we're basically getting to the point where like once you've approached materials cost as like a dominating factor of the cost of your device, you have to either switch you basically have to switch materials if you want to get any improvement, or try and squeeze efficiencies out of the materials you're currently using.
Okay, well, I think this sets us up well. So, I mean, so lithium is the dominant battery architecture for all these reasons. We're approaching the cost of input materials, all of the development design pressures on the cathode, because that's the limiting factor. So now where do you guys come in? What is the Oros angle on this?
Yes. Okay. So our angle is a new cathode material primarily. So instead of NMC, we are using lithium oxide. So you get sort of two benefits here. One is that oxygen is much lighter than nickel manganese cobalt oxide. And the second benefit is you get two lithiums on one oxygen instead of one lithium per nickel oxide. And so mass wise, like you're looking at about 11 times lighter on the cathode level. Now you still have to incorporate the anode and the electrolyte and everything else, but ultimately, like Oros's plan is to get as close to the theoretical energy density of lithium oxide and then minimize the amount and mass and cost of everything else in the battery. So you want to make the battery look as close to the energy density as of the materials as possible.
Yeah. And this makes a lot of sense. I mean, based on our first order intuition of like, it's the mass to charge ratio. Here we have these massive nickel atoms and these oxygen atoms that aren't really doing anything. And we store one lithium. Now we store two lithium for one oxygen. But now this is your willingness to show this on a slide kind of tells me that there's a lot more going on than just this. I mean, this can't be the full secret. So I mean, does this approach have, I mean, you know, maybe it speaks to the current methods, but like, does this have, say, more negative side chain reactions or side reactions that are kind of deleterious to its long-term performance? Does this not charge and discharge nicely over time? Does that have higher or lower Coulombic efficiency?
Yeah, so there's a lot there to unpack, but basically, the first challenge is like this material is much more sensitive to water. So your manufacturing processes need to be really buttoned up. You need to like make sure that basically to like a ppm level of water, that no water is getting into your materials, because it will start a chain reaction and basically render your battery useless. The other challenge, like you said, there are still side reactions. Like with any new battery chemistry, you tend to start at zero, but I think the nice part about this chemistry is it's still lithium, it's still a metal oxide, so you can tap into a lot of the work that's been done thus far on additives and electrolytes. So we've been able to shortcut, I'd say, like 75% of that development, but like Coulombic efficiency is still definitely a challenge. And then like the other part of it is lithium oxide is relatively insulating compared to lithium nickel oxides, because that nickel confers electrical conductivity. And so oxygen doesn't quite do that as well. So you have to sort of change the electrical conductivity through dopants or coatings, things like that, to get it up to like high enough power for many of these applications.
Yeah, I'm now thinking about this. So it's the lithium ions that are shuttling back and forth between the cathode and the anode.
Yep.
And nickel oxide on itself, I could see this being like a solid material of some kind, even if the lithium is gone. But lithium or dilithium oxide, like oxygen, isn't like a solid substance at standard temperatures and pressures, nor does it form a metal. It's like a horribly reactive thing. So I'm guessing that's another challenge where
it is. So the history of lithium oxygen is like, the first lithium oxygen battery was developed in the 70s by Lockheed Martin. And basically this was where you take oxygen from outside of the battery, and therefore don't have to carry the mass of it. And then you have a lithium metal anode, and you sort of combine the lithium and the oxygen in this carbon structure on the cathode. So incredibly complex. It's not really reversible, so you can use it once. It's like in that way, it's almost like a fuel cell, but very, very high energy density. So the trick with our chemistry is we start with lithium oxide, and there are two other lithium oxide compounds that you can cycle to. So as you pull lithium off, there is intermediate compounds before you reach oxygen gas. So you have lithium peroxide, so it's lithium 1, oxygen 1. And then there's lithium superoxide, which is lithium 1, oxygen 2. So the structure changes a little bit to accommodate that. And also oxygen can accommodate different valence states. So oxygen can have a -2 charge like it typically does. It can also have a -1 and also a -1/2. And so as long as you don't pull all of the lithium off, it'll stay a solid, and you can use it in a much more reversible way. You also can seal your battery completely to the outside, which is absolutely necessary for any sort of cycle performance. The downside is you now have to carry the mass of the oxygen, and so it's not quite as light as it could be. So the numbers are like, so I have this slide. Here it is on this on the right here. So lithium oxygen is actually higher energy density than gasoline. In its purest state, it's 13 kilowatt hours per kilogram. The materials we are working with are closer to 4,000 watt hours per kilogram. So it's about a third of the energy density of gasoline. And so,
this plot is very misleading. Why the super tall chart, is that 11.944 or is that 11,000?
11.9. It is 11,000. It's
Okay.
11.944 kilowatt hours per kilogram.
Versus 120.
I think they should have put a comma there, but to have the numbers in the same scale, but yes. Okay. But the lithium ion batteries are also, this is a bit of an old chart, like they're closer to 300 to 400 now, but basically, like the chart on the right is sort of an illustration of why this matters and like why we're even using lithium ion batteries today. And it's basically that like internal combustion engines in cars are very inefficient. So you get about 20% of the energy from the chemical fuel to the wheels. Most of it's lost as heat. Whereas in an electric car, you can actually recover it with regenerative braking. And so you end up closer to 89, 90%. And so for the break-even point, basically like 20% of roughly 12 kilowatt hours per kilogram is 2,600 watt hours per kilogram. And so, if you have a cathode material that can do 4,000 watt hours per kilogram, and then you say, okay, well, you have to include the anode and you have to include the electrolyte and all this stuff, then maybe you can get to 2,600 at the battery level.
Okay. I mean, 2.5 kilowatt hours per kilogram. And that's like a 10x over where we are now with like this 250 watt hours per kilogram.
Yeah. Like 3,000 would be 10x the Tesla 4680. A lot of batteries are 250 to 300.
And it is the difficulty now. So for your targeted cathode chemistry, so super high power density, it's a much smaller sort of molar mass per lithium ion that it can accept, like a sponge. Is the next challenge then to engineer it to have like, or what would be the next performance metric to target to kind of, because I guess you're starting with this high energy application, it's perfect for defense kind of stuff. If you can crank on this next performance metric, then you kind of unlock this next market. Like, what would that be?
Yeah, so I think like for us, so we're at like 100 cycles right now. So that's great for military applications. The next step is definitely like getting higher cycle life. We need more nines of efficiency to get to automotive and grid storage. And then specifically for grid storage, so this is like some of our internal data. So you have a charge. This is the top portion there is the charge portion, and then the top right corner is where it switches to discharge. And so you can see you lose a lot of voltage. So for specifically grid storage applications, we need these curves to be much closer to being on top of each other in order to get like high round trip efficiency. For a lot of like mobility applications, it doesn't really matter because ultimately like it matters in the sense that you want to store as much energy as possible, but they don't really care as much about like losing mass.
Sorry, is that you or me?
I think that's you.
Okay, so 1 second. Okay, my mistake. I had do not disturb, but anyway. Okay, you can hear me okay?
Yep, all good.
Good, we're back. Okay,
so yeah,
cool.
I was just saying it's not as critical. It's still critical because like that lost energy goes to heat, but that's a much more manageable problem for like an EV than it is like losing a third of your energy that you put in for like grid storage. So yeah, so I'd say like that's so cycle life, and for the immediate applications, it's like cycle life. Power, like we're doing pretty well on power. We're like at low C rates, we're at parity with lithium ion. It's just for like very high power applications. We maybe need to improve a little bit there. So I think like for us, it's like right now it's power and cycle life, and then down the road it'll be like this voltage challenge.
From the chemistry perspective, what is driving the voltage drop as you discharge?
Yeah, so it's almost everything. It's like the purity of your materials, the quality of your cell construction, the uniformity of your electrodes. So how well are you mixing and dispersing the particles? What size are they? How well does lithium diffuse in and out? What's the conductivity of your electrodes? How well are they pressed together? And like how good are your welds? How good is the, like internal vacuum on the cell? So yeah, so even like on this slide, you can sort of see we've sort of inched up the curve. So some of those on the bottom portion, the lines that end lower are some of our earlier cells, and then we've sort of inched the curve up.
In thinking about our like electrochemical water tower analogy, I'm thinking like, so we're taking charges from this high potential, and they're going to fall to the bottom first, but they start to kind of like stack up on top of each other to kind of occupy those lowest energy states first. And so as it fills up more and more, the height difference, it's like Tetris blocks. I'm thinking like the height difference decreases overall as well. So it's like the last charge to fall through the electrochemical potential can't fall as far as the first charge because I guess the energy states are kind of occupied now, and getting more, I guess, getting a broader reservoir. That's all about this cell construction manufacturing of getting good seals, good welds, good compression, that kind of stuff.
Yes, yeah, that's a good way to articulate it. There's the thermodynamic. There's also a kinetic component to it. So I think there's the stuff that's easier to do is generally kinetics. So this is smaller particles so that lithium can diffuse to the center faster.
Mm.
This is like, you know, more compact electrodes, so you're calendaring them tightly. Um,
And
yeah.
and so this is this thing about battery performance being temperature dependent, right? Like cold batteries don't work as well because the ions are less
Yes.
mobile at that low
Yep.
temperature. So a hot battery can kind of, there's greater ion mobility. You can more fully drain the reservoir of charge or more fully fill the lower reservoir as it
Yep.
discharges.
Yep. It Yeah, that's exactly right. There is a drawback at higher temperatures though, which is like you accelerate any side reactions. So
Okay.
people actually use that for accelerated cycle testing because if you do 2,000 cycles in a car that typically is like 5 to 10 years of usage, and so you don't have like 5 to 10 years to do one iteration on your battery, right? So you have to figure out ways to accelerate it, and high temp testing is one of those.
Mm-hmm, mm-hmm. Interesting. So for you guys, you're optimizing this cell chemistry and the cell construction itself, and that is this flat sheet, this thin layers of material. Once
Right.
you kind of have a chemistry, architecture, or composition you like, it is from that point much simpler to kind of roll it up into a cell, put that into a battery pack. So it's really like you're tackling the hardest part, the most upstream part from all downstream performance.
Yes, exactly. Yeah, I mean, we're trying to do the most high leverage thing we can do, which is like target the limiting factor within the limiting factor within the
Totally.
limiting factor. It's like
Yeah.
you know, cars are limited by their packs, packs are limited by their cells, cells are limited by their cathodes, and so that's what
Right.
we're targeting.
And I'll give you kind of open mic to kind of vent. Like, what is this graveyard of past battery companies that have come and gone and raised huge amounts of money, and then but still we're like, what is your take on this, like this battery landscape? Because I guess many people have tried many different, and I hear of things today like lead or iron air batteries and
Oh yeah.
you know, graphene superconductor or supercapacitors and stuff like.
Yeah, I think there's like an old I think it's like an old Edison quote, and it's like something like, "How do you know like your battery supplier is lying?" It's like his mouth is moving. So I think like as far back as like Edison's time, like snake oil salesmen have been attracted to batteries for whatever reason. I think it's a testament to like sort of the fundamental promise of batteries, but that it has been a feature. Not to say that everyone in the battery space is a snake oil salesman. I think like many people are well intentioned, but I think end up like going into it without realizing the difficulty of what they're trying to do. So I guess like my characterization of the last 15 years or so is like there have been it's 10 years ago it was almost entirely anode material plays. So you were looking at lithium metal anodes, silicon anodes, and solid state electrolytes, which are um, they're basically an enabler of lithium metal anodes. And so like I think all of these things are um, we're basically trying to solve a problem that was not the high leverage thing to do. So we talked quite a bit about how graphite was and is 2 times the energy density of the best cathode materials out there. And so you can optimize, you can get a better anode, but you will only become more severely cathode limited. So there's actually a slide in here about this. So the bottom right there, that graph basically details like what sort of energy density can you expect if you go to massive cathode loadings, which is what you need when you get higher and higher energy density anodes. And so you can see it tops out around where we're at today, which is like 400 to 450. And so like, I think that's like sort of the first mistake that that cohort of battery startups made. I think in more now, I guess like one note on silicon. Silicon is here; it like works. I think lithium metal broadly is the challenge is it's thermodynamically unstable. So lithium wants to react with everything around it. And so the fundamental challenge for lithium metal battery companies is safety. And to date, no one I've seen has solved this, including the solid state companies. Silicon, however, has been used in commercial cells for 15, maybe even 20 years now. So Tesla has been using 7 to 9% silicon in their anodes for like at least 10 years. And it works really well. The challenge was always like swelling, but especially with companies like Sila and Group 14, that challenge has more or less been solved. So Group 14 and Sila, you can do 100% silicon carbide with little to no swelling, and you can get 1,400 cycles with it. And it's 5 times the energy density of or capacity of graphite. So you're at 1,900 milliamp hours per gram instead of 350 for graphite. So the main challenge for silicon today, though, so they've solved the safety more or less. They've solved the performance, but the one remaining challenge to solve for silicon is the one that was like maybe the most promising in the beginning, which was cost. So the way that people have solved it today is they use silane gas, and they essentially, it's a chemical vapor deposition process. They impregnate hard carbon particles. They impregnate these hard carbon particles with silicon metal. So they vaporize silane gas, and these nano little dispersions of silicon deposit inside the pores of a carbon sphere. And so this solves your performance problems, it solves your swelling problems, but it's extremely expensive. So the cost targets are like $150 a kilogram. Graphite is like $5 to $10 per kilogram. So you're 5 times the energy density, but you're 20 times the cost. So, you know, there are, we are working on one of the potential solutions for this. So it's basically using a different silicon carbide process and using metallurgical silicon as an input, which is used in chip fabs. So it's very cheap. We've demonstrated equivalent capacity, not quite as high cycle life yet, but I think there's a pathway there. And but it's one of those things where there's still some swelling. It's likely that you're not going to get to 100% silicon in the anode. So there's an economic use case for it, but it's not the sort of thing that it will go everywhere and replace graphite in everything yet.
And so for people looking to, you know, kind of invest into this like next generation of battery development, but maybe have been burned on these past battery companies that didn't, you know, what would be your advice to them to kind of understand like how to make a good judgment here, or what to watch for, what to look for?
Yeah, I mean, it's very hard. Like, it's very easy to cherry pick data. There's like so many different performance requirements. I think, you know, I think that like, just because I think like the first thing you should look for is like, is it a cathode material? I think if it's not a cathode material, it's got to be a silicon, and it has to be like economics focused. On the cathode material, you have to make sure that there are two pieces in place. It has to be like the materials need to be scalable and the process needs to be scalable. So I think people generally do the first one well and the second one poorly. So, one other competitor group of technologies is lithium sulfur. Sulfur is dirt cheap. It's a byproduct of the oil industry. But the way people typically make these cathodes is they mix sulfur with 50% graphene or carbon nanotubes, which are extremely expensive on a per kilogram basis. And so that's like one example of like non-scalable materials. In terms of non-scalable processes, I think like atomic layer deposition is non-scalable. Chemical and physical vapor deposition are non-scalable. Like it really needs to be a bulk process. It can't be sort of batch processing. So, continuous high throughput manufacturing processes. Yeah, I think those are the broad strokes.
Right. So think about, what are they optimizing on cathode? If not, they're probably going for economics on silicon. And then past that, do they have like practicable economic methods of scaling up production of cells at volume?
Yep, exactly. And then I think like the other thing, most investors already do this, but like it has to be much better. It can't be like, I think there was some investors looking at like cobalt-free cathodes, but no performance benefit. And I think that's like, you're kind of like picking up pennies in front of a steamroller.
Right.
If you're like thinking like 5% better than lithium ion.
And you're targeting like the upper bound is this 10x energy density performance improvement, which is maybe for like a very optimized kind of N of one prototype, I guess. But maybe as you scale to production, maybe that remains an 8x or a 7x or something like that.
Yep, I think that's doable. I think the numbers, if we hit all of our tech development milestones over the next few years, I think 5x is conservative.
Okay, that's awesome. And I mean, what would a 5x higher energy density lithium ion battery do for us? Because that's one of these big civilizational levers, right? Like that's probably the bottleneck to something like these electric flying car taxis or something like that.
Yep, exactly. So I think like what it looks like is like you could have coast to coast ranges for Teslas. You could have electric flying cars or flying taxis. I think like home energy storage becomes ubiquitous and very cheap. I think backing up almost everything in your house. And I think like I think broadly electric aviation becomes possible. People debate at what energy density, but some people put it as low as 400 watt hours per kilogram. Some people it's more like 700 or 1,000. But above 1,000, it's electric aviation is for sure possible in a big way. The only segment of electric aviation that likely wouldn't, or of aviation that wouldn't go electric, is sort of long haul flights.
Right. So this is like, I think of this as like a transoceanic, like commercial airliner, something like that.
Yeah.
But you could have regional transportation, like point to point, like over a few hundred miles or between cities, like maybe SF to LA or something like that.
Yep. I think regional is definitely doable. And then I think I put some, there's implications for AI data centers, defense applications. Like drones become very attractive for all kinds of jobs. consumer electronics like AR and VR are really limited by their batteries today.
Totally.
And the more fun sci-fi applications are like, a lightsaber, you know, man-portable laser weaponry, and different types of electric aviation, whether it's like ionocraft or plasma pulse jets or things like that.
Yes, this I love this slide so much. It would unlock for me. I got to find someone to talk about this, but this electric arc jet thruster, where you just have so much energy on board, you just ionize air, and that becomes your propellant. So you have like, it's like a crazy high specific impulse jet engine, but you need huge amounts of current flowing. I'm hoping from your batteries. As an investor, I am, absolutely. And we can close with this too, because I'm curious. Like, it's been maybe a year and a half since I visited you guys down in Miami. What's the state of affairs in Oros today? Kind of what's top of mind? I know when I visited, you had a cool laboratory bench set up. What's going on the inside, and what's next?
Yeah, so we are in the middle of a fundraise. We're basically raising to scale up our materials production and put them in commercial cells and start selling the cells. So we have over double the capacity of today's lithium-ion batteries, about 100 cycles so far. So targeting mostly drones for those cells, and then basically we're continuing to push the capacity, continuing to push the power, and I think we should be able to launch commercial cells mid-year. We're starting to make prototypes for folks now.
So you've already wandered. You've done like the hero's journey through this like nightmare of electrochemical design trade-offs. You've kind of landed at an optimized cathode materials design choice, and now it's a matter of just getting better at, I guess, producing these things in a reliable, scalable fashion.
Yep. That and the fundraising aspect of it.
Yeah, absolutely. Well, if anyone watching has questions as to why I invested, reach out, ask me anytime. Gladly would give them my thesis, my Oros thesis. And yeah, thanks, Ethan, so much for taking time. This has been great. I hope in the future we can get you back on with the lightsaber in hand or something.
Definitely.
Right on.
Thanks, man. Andrew.
Cool. Talk to you soon.
Take care.
All right.
Bye-bye.
All right. See ya. Cool. That was Hyperstition number 10, high energy density battery storage for the future. I think we all want lightsabers. We all want banshees. And energy is going to be a big theme this week. Tomorrow's talk is going to be around energy-based currency and how do you optimize the financial incentives of a capitalist economy with the #1 barrier to growth, which is energy, and that I think is energy-based currency. So I hope you join us then. And until next time, keep learning this hardcore science, because it'll actually determine what makes sense and what is fake or real into the future.